In today's basic organic chemistry class, we'll be looking at elimination reactions of alkyl halides. Elimination reaction will mean loss of elements from starting materials to form new pi bond in the products in the presence of Bronsted-Lowry base. The nature of pi bond formed is determined by the nature of alkyl halide. If it's haloalkanes, we are going to form alkene. If it's dihalide, we are going to form alkyne. Alkyl halide, in the presence of tertiary butoxide and sodium ethoxide, their corresponding alkane were formed. It is formed by dehydrohalogenation, and this dehydrohalogenation is a beta elimination reaction. Remember, from reactions of alkane, when hydrogen halides are added, we call it hydrohalogenation. So in this case, we are removing that hydrogen halide that was added in alkane. Why is it called beta elimination? It's because the hydrogen that is being abstracted by this base is from beta carbon. Remember, the beta carbon is the carbon after the carbon that bears the functional group, and the functional group in this case is the halide. So the next carbon here is the beta carbon, which is bearing the acidic hydrogen that the base will come and take. Why halogen is a good leaving group? So as soon as base takes away this hydrogen, then halogen leaves. The bases employed in these elimination reactions are negatively charged oxygen compounds such as hydroxide or alkyl derivatives such as alkoxide. When there are identical beta carbons, one compound is being formed. When there are different beta carbons, we have two compounds. Among these two compounds, one is more stable than the other. We have one sigma bond and pi bond, while in alkyne, we have two pi bond and one sigma bond. These alkenes are classified according to number of substituents attached to this carbon that is connected to double bonds. So when only one substituent is added, we say they are monosubstituted. When there is two, they are di. Difference between alkane and alkene is because in alkane, rotation at 180 degrees is possible. It means that I can move from staggered to eclipse. I can interconvert by rotation. But in alkene, because of the double bond, rotation is not possible. So interconversion is not possible. Rather, we have isomers, which are cis and trans, because of restriction in rotation. Example of the isomers. The cis and trans are not mirror image. It means that they are not the same. So in terms of reaction and everything and instability, trans is more stable than cis. Because in cis, the substituents are one-sided, just like putting weights on one side of a bench. That's what happens in cis. But in trans, the weights are balanced at both sides of the bench, making it more stable. The possibility of having cis or trans is dependent on the substituent on this carbon connected by double bond. The substituent must be 4 different connected to the double bond. So this carbon that bears the double bond is going to have different substituents for there to be stereoisomer. It means that carbon 1 will have one different substituent, x1, x prime and x will be different. Then y prime and y must be different. So if I have x and x prime to be the same, it means that this compound will not have stereoisomer. And if I have y prime and y to be the same, y s prime and s are different, the compound still will not have stereoisomer. There must be different substituents between s prime and y prime and x and y for this compound to exhibit stereoisomer. In these stereoisomers of cis and trans, the most stable is trans because the substituents are far apart, so there are no steric interaction. Unlike in Cs, the substituents are facing the same place. There is high tendency of steric interaction, which bring about the stabilization and reduces reactivity of cis isomer over trans isomer. The stability of this alkene is increased by virtue of the number of R, which is alkyl, attached on the carbon that is connected to the double bond. So the more the substituent, the more stable. It's because sp2 has more X character than sp3. Hence, sp2 can accept more electron density. So electron donating group like alkyl will stabilize sp2. Hence, di are more stable than mono, and tri are more stable than di. This is the reason why monosubstituted butene is not as stable as di-substituted. And in that di, cis is less stable than trans. So stability increases from mono to cis to trans, because in trans there are fewer steric interactions. Trans is more stable than cis. Now we're talking about mechanism in elimination reaction. In elimination reaction, we have two mechanisms, which is E1 and which is also similar to SN1. E2 similar to SN2. E2 mechanism is talking about bimolecular elimination. SN2 is bimolecular substitution. E1 is unimolecular elimination. SN1 is unimolecular substitution. Starting from E2 mechanism. This E2 mechanism is a second order kinetics, meaning that the alkyl halide and base are responsible for the rates of the reaction. This reaction is concerted, meaning that as the old bond is being broken, the new one are being formed at the same time. That's why the reaction is called to be concerted. Of mechanism of E2 reaction. The base, as the base is taking this beta hydrogen, the bromine, which is a good leaving group, will leave and new bond is formed immediately. This happens at the same time. From the energy of the reaction, we can understand that in the transition state, bond broken and bond formation are occurring at the same time. That's why we are calling it a concerted reaction. That's why we have just one energy of activation for the reaction to occur. E2 and SN2 are similar in the identity of base, the leaving group, and how solvents affect the rate of their reaction. So in E2, the rate of the reaction increases as the strength of the base increases. E2 is favored by strong bases or sterically hindered nitrogen bases such as DBN and DBU. Good leaving group is going to enhance E2 reaction. What determines a good leaving group? The halogens are the leaving group. The better the leaving group, the faster E2 reaction. And leaving group increases with increase in an atomic number. So the higher the atomic number, the better the good leaving group capacity of halogens. Finally is the polar aprotic solvents, which also enhances the rate of E2 reactions. So three things enhances the rate of E2 reaction: the strength of the base, good leaving group, and polar aprotic solvents. When compared with SN2 reaction, E2 reactions are better with tertiary, while SN2 reactions are better with primary. These are where SN2 and E2 differ. Remember, in terms of base, leaving group, and polar aprotic solvents, they are similar. They only differ in the alkyl halide. Primary alkyl halide favors SN2, while tertiary alkyl halide favors E2. The Increase in E2 reaction rates increases with increase in alkyl substitution. That is why tertiary favors E2 reaction. In a typical example, we have primary alkyl halide and tertiary alkyl halide. Primary alkyl halide is going to form, in elimination, is going to form a less stable monosubstituted alkene, while tertiary is going to form disubstituted, which is more stable, and that is why tertiary is more preferable for E2 reactions. E2 mechanism are second order, meaning that the rate is determined by both the alkyl halide and the base. The mechanism is one step because it is concerted reaction, and the more substituted the alkyl halide, the faster the reaction rate, meaning that tertiary is faster for E2 mechanism than primary, but all are possible. Strong basis favors E2 mechanism. Good leaving group favors E2 mechanism, and polar aprotic solvents. Therefore, we are going to determine the most stable of the product formed by elimination reaction of E2 mechanism. The major product is the most stable product, and the most stable product is the one that is more substituted. That's why tri-substituted is more stable than di. Now, how do we understand the less stable ones? Remember, we'll talk about substitution. When a compound has more than one beta carbon, that compound is going to form two isomers, and the most stable isomer is the more substituted and is the one that is isolated. That is termed the major product. Using Sesef rule, we can also obtain a more stable product using stereo selection. In that stereo, we form two products. One is trans and one is cis. The trans become the most stable over the cis because in trans there is less steric hindrance than that seen in cis isomer. Unlike E2 mechanism, E1 mechanism is determined by just the alkyl halide. It is unimolecular because it's only the alkyl halide that determines the rate of the reaction. It is two steps because the first step is transition state, which determines the rate of the reaction, and this is where alkyl halide is involved. While the first step is when a base abstracts the alpha hydrogen to form alkene. Example of E1 mechanism. The first stage is slow step where the alkyl halide leaves to form carbocation. The second stage is where a base in this case is a weak base. Weak base is going to come and abstract the acidic hydrogen to form alkene. In energy diagram, we realize that the transition state has higher energy, so that's the energy that must be overcome for reaction to occur, and that is why it is a rate determining step. Comparing the rate of reaction in terms of alkyl halide, tertiary is more favorable for E1 reaction. Primary never occur. So for E2 reaction, both are feasible, but tertiary is more reactive. But E1 reaction, tertiary is more feasible, primary is not possible. Using Sesef rule, the same way we predict the stability of product in E2, that same way we are predicting the one of E1, because the more substituted a product is, the more stable the product becomes. That's why tri-substituted is more stable than disubstituted alkene. The rate of E1 mechanism is first order, meaning that the rate is determined by only the alkyl halide. So for a reaction kinesis to be first order, it means that the rate of the reaction is determined by the alkyl halide. It is two steps because it involves carbocation first before abstraction of the beta hydrogen to form alkene. In this case, the more substituted, the better, meaning tertiary is more feasible for E1, primary is never feasible. Unlike E2, weak basis favors E1. Just like E2, beta leaving group favors E1. Unlike E2, polar protic solvent favors E1. Now, comparing SN1 and E1 reaction, they have exactly the same first step, which is formation of carbocation. What differs between them is what happens after carbocation is being formed. In SN1, a nucleophile will come and attack that point of carbocation, that is that position where halide left, nucleophile replaces. That's what we call it substituting. While in E1, a base takes beta hydrogen to form a double bond in E1 reaction. In terms of E2 mechanism, we have two ways of arranging this carbon, hydrogen, and halide. It can be seen periplanar or anti-periplanar, but anti-periplanar is preferable because the substituents, the bulky groups, are on opposite side, they are in transconformer. Because of that, there is least interaction, so steric effect is fewer here, so it's easier for leaving group to leave and it's easier for incoming substituent to bond. So E2 elimination is easier in anti-periplanar geometry than in syn-periplanar geometry. In comparison, E2 is much more useful than E1, and strong basis favors E2 while weak basis favors E1. Primary, secondary, and tertiary alkyl halides are possible in E2, but in reactivity, tertiary is more. But in E1, primary does not occur because the carbocation they form is highly unstable. So that is different between these two mechanisms. It's mostly used than E1. Now, we can form alkyne by double elimination reaction. So we are going to do two hydrohalogenation elimination to move from alkene to alkyne. This is possible only using vicinal or germinal dihalides. In the presence of a base, vicinal or germinal dihalides will be eliminated. So hydrogen halide will be removed twice from vicinal and germinal dihalide to form alkyne. Now, these stronger bases are needed. These bases are needed because it is difficult to remove this hydrogen halide after alkene is formed because of sp2 is stronger than sp3. This reason made us to need strong base like sodium amide or tertiary butoxide in DMSO. Like I said previously, the reason is because after removal of first hydrogen halide to move from saturated to unsaturated alkene, to move from alkene to alkyne, there is need to use a stronger base because the bond of alkene is stronger than the bond of alkane. So a stronger base is needed to abstract this hydrogen that is connected to double bond. Hence, the need for tertiary butoxide or sodium amide. This the typical example of dihalides to form alkyne. Remember, because we are doing double dehydrohalogenation, we are going to use two equivalents of base to remove two equivalents of hydrogen halides. Now, if you're asked which of the following can yield alkyne, go and look for vicinal or germinal dihalides. How do we predict whether a compound is SN1 and SN2, E1 or E2. Now, when there are good nucleophiles that are weak bases, substitution reaction will be favored over elimination. Certain anions give a product that are substitution because they have good nucleophiles that are weak bases. These nucleophiles can be bromide, can be iodide, cyanide, or carboxylate. So when I see this in a reaction, instead of elimination, substitution reaction will predominate. Now, bulky non-nucleophilic bases such as tertiary butoxide, DBN or DBU are going to favor elimination over substitution reaction. So when I see these bulky strong bases, elimination will take over instead of substitution. Let's predict the mechanism of these reactions. This is a tertiary alkyl halide. In that case, we are having, with strong base, we are going to get E2 mechanism with tertiary. Remember from the previous slides, tertiary is favored by E2 mechanism, while SN2 is favored by primary alkyl halide. Then the same alkyl halide, same tertiary alkyl halide with weak nucleophile or with weak base will form SN1 and E1 products. Remember, tertiary is being favored by E1, while tertiary is still favored by E2. But in E2, strong bases favor E2, while weak bases favors E1. Now, with primary alkyl halide, we are going to have substitution reaction instead of elimination, because in the presence of strong base, primary alkyl halide, substitution is favored than elimination, while tertiary alkyl halide favors E2 in the presence of strong base or strong nucleophile. But when I have primary alkyl halide and I'm using strong or sterically hindered bases, E2 will predominate. This is secondary alkyl halide. In the presence of secondary alkyl halide, when I'm having strong base and nucleophile, I can have E2 and SN2. But when I'm having sterically hindered bases, E2 will predominate. When I'm having weak bases, I'm going to have SN1 and E1 products. Go through this class again, ask your question. There will be self-assessment question after this. It's going to cover the alkyl halide 1 and this alkyl halide 2. Use it to know how much you understand this class. If you're able to answer them, you know you're good to go. If not, go back to the slides and go through it again. Remember, the more you listen to this slide, the more you understand. Wishing you success in your 213 journey. Thank you.